So 23. Give me the big number.
Whatever.
0, 1, 2, base 5, divided by 2, 3.
Okay. There's one. The other one?
2, 0, 1, 2, base 3, divided by 1, 2, base 3.
Who wants to do? Which one do you want?
Either one.
Doesn't matter. Who wants the other one? Okay. Tricia, let's have you wait. I'm going to let her talk out loud, and then I'll let you walk us through it as well. Okay, so go ahead.
Okay, so the first thing you have to do is find all your multiplication facts of this one. So you have 23 base 5, and I'm just going to skip base 1 or times 1 because it's just 23. So I'm going to
Just
start
2,
with
3.
times 2. Yeah, 2, 3 base 5. Okay, so then 2 times 3 is 6 in base 5. It goes in once with 1 left over. And then 2 times 2 is 4, plus 1 is 5, which is 1, 0. Okay, so then 2, 3 times 3 is 9, which is 1 with 4 left over. And then 7, which is 1 with 2 left over. And then 2, 3 times 4 is 12, which is 2 with 2 left over. And then 8, 9, 10 is 2 with 0 left over. And then you don't have to go past that because there's no 5 in base 5. So then 2, 3 goes into 4, 3 once. Subtract. And then this is 3. And this is 4.
Can you slow down? Yeah, can you slow down? I'm still on the 200 minus 124.
Okay, so for this one, you have to like borrow or exchange, make equivalent exchanges. So like, I can't exchange anything from here, so I have to go all the way over here. And I take 1 from this one, and that's 5 here. And then I take, from this one, I have to take 1, which is 5 here.
So it's 5 for both zeros.
It would be
Yeah, but then I have to
1/4.
take 1, 5 from here, or 1 from here, which gives me 4. So this is actually 4 now, because like, it's like when you subtract from zeros, you have 2 zeros, you have to keep borrowing. And then it's the same thing down here, you don't have enough here, so you have to borrow from here, which gives you 0 here, but then you add 5 to the 1, which is 6.
What else? Okay.
And then you don't have to do 1 because you know it's 2, 3. It's just so that way when she goes up.
Okay, so I brought the 2 down.
Why is it 6? Because it's 5 plus 1.
Because you added 5 to the one that's already there.
Right, but it's still 6.
Right, but you like
So you could say
borrowed 5. Yeah, you could say like 1, 0, or 1, 1.
You could leave it 1, 1 as long as you knew that wasn't 11, that it was 1, 5, and 1 left over is 6.
You kind of convert it to base 10.
Yeah, it's easier for me to subtract 2 from 6 than from 1, 1.
There was 1 there, and she exchanged for 5. That makes 6 now. Because she didn't have enough to take 2 away from 1.
Okay, so then I had 4 there, and I brought the 2 down, and 2, 3 will only go in once. So then I'm going to make equivalent exchanges again, so I have to borrow 1 from here. And when I add to this, it's like 1, 2, but I'm just going to say 7. She's using a 4. So then I have a remainder of 1 4.
Now, you may have not had time to check your answer, but how would we have done it?
You convert everything to base 10.
Convert everything to base 10, divide, and then convert your answer to base 10 to see if it works. Any other ways?
Just multiply the answer by dividend.
Multiply the quotient times the divisor to see if, oh, and then add the remainder to see if you get the dividend. Multiply this times this, then add this to it, and you should get that if you did it right. Thank you.
Brother Piper, I got a question.
Yeah.
How come like the 2, 3 base 5 times 2 is 101 and then the 2, 3 base 5 times 3 is 124? And like those two are relatively close. I understand multiplication on, that's not what I'm asking. But what I'm asking is how come when you go to the 2, 3 base 5 times 4, it jumps up so much because it looks so wrong.
Well, timesing by 4 is twice as much as timesing by 2, and look at the answer. Does that help at all?
Yeah, it helps. It's just like when I was doing the test, I was so worried because it looks so completely wrong because it's so much bigger than the other two numbers.
And it really isn't.
It's just because it's not base 10, it's base
Yeah.
5. See, like you can't have anything bigger than a 4.
It's almost done.
Yeah.
By the way, if you like addition better than multiplication, instead of multiplying to get your facts here, you could do 2, 3 plus 2, 3, right?
Which is what I do.
Which is 3 plus 3 is 6, which is one group of 5 with 1 left over. And then add these, you get 5, that's 101, right?
Yep.
So this would here be times 2 because I've added 2 2's. Then you add another 3 on. That gives me 4, 2, 1. So that's times 3. And then I add another 2, 3 on and get with, let's see, 7 would be one group of 5 and 2 left over. And 5 would be 0 with, okay, this is times 4. You can do it this way if you prefer adding. And then you can use these numbers whenever you get your remainders here to see if how many times it's going to go in. That helps. Okay. All right, Tricia, if you want to.
We just keep it and do it in the base, so it'd be 14 base 7 times 2 base 7, and then it'd just be 14 times 2 base 7. Everything would be in that base. That makes sense. So that's why I makes it more complicated.
So I started out by finding the different factors. And you can only go to 2 because it's base 3. So then I go over here, and 12 goes into 20 one time. So I come back over here, and so I write 1 up here, and then 12 times 1 is 12. And then I have to subtract that. And you can't subtract 2 from 0, so cross that out. And it's base 3, so 3. So then 3 minus, that's a 1. 3 minus 2 is 1, and that's 0. And then bring down the 1. And then 12 cannot go into 11, so that's 0. And then bring down the 2. And then 12 goes into 112. And you look back over here, and it definitely goes into it 1 time. So if you look at 2 times, it definitely goes into it 2 times. So then write 2 up here. And then 2 times 12 and base 3 is 101. And then you subtract that. And 1. And then you can't go into it anymore, so it's remainder 11.
Questions? Everybody see why she put the 0 here? Because even after we brought this down, it wouldn't go in. Okay? Gotta have that placeholder. Okay. Let's talk a minute about your experience yesterday with the curriculum of how having students develop their own method to divide fractions. The division models are what? You got them down? The repeated subtraction.
Partition.
Partition. Or sharing. Repeated subtraction can be called measurement. And missing factor model. Okay? Again, these are ways of thinking about the problem. Let's go over these. If I have 12 divided by 4 equals, and I want to model it this way, what do? Repeated subtraction.
You continually subtract 4.
I've got 12 blocks in my hand, and I what?
You take away 4.
Repeatedly take off the size of the divisor. When am I done? When I don't have any more left in my hand, what is the answer?
How many groups do you have?
How many times I broke the 4 off? How many times I broke this off? We okay? All right. So we were doing problems with some fractions. And sometimes these fractions get a little bit difficult to do because here's the one we had here, 9 divided by 1/3. And none of you had any problems with this when you drew pictures. You said, I've got 9 packages of cheese. I need 1/3 of a package to make a pizza. How many pizzas did we make? And you drew your 9 packages, divided them into thirds, and then you could make what? 27 pizzas. Well, let's take this and do it with this model. You ready? I've got what in my hand? 9. What am I going to do? I'm going to break off 1/3 of one. Put it here. Break off another 1/3. I'm going to keep breaking off thirds until I get when? To 0, when I have nothing in my hand. How many thirds did I break off? 27. Does everybody see how that model works there? Okay. Let's take the partition model with this one. How do we do it?
Can you share it?
We're sharing. Yep. So I've got 12 in my hand. And what?
And you would make 4 different groups by putting one at a time.
I've got 4 bins here, 4 partitions, 4 places. That's who I'm going to share with. And I'm going to start by just dropping one in each one, right? 1, 2, 3, 4. Am I done? No, I still have some in my hand. 1, 2, 3, 4. Am I done? No. 1, 2, 3, 4. Now I'm done. What is my answer?
How many is in each group?
How many in an entire group, right? Everybody with me? Okay. Let's take this one here. partition model. I've got 9 in my hand. I'm going to share it with a third of a group. So I can't even start going like this because there's not even a whole group. Okay? I'm going to share it with just a third of a group. So guess what? That third of a group gets everything I've got in my hand. That's what I'm sharing it with, right? The answer is what? How many in a whole group? Well, if a third of the group holds 9, the whole group holds... Can you wrap your head around this one? Holds 27. Here's my 3 groups. Here. Or excuse me. Here's my group, and I'm going to share it with a third of a group. I'm going to put it right here. All 9 of those goes into this third of a group, right? The answer is how many are in a group. That's what our answer is to the partition all the time. How many in the group? Well, if there was 9 and a third, there'd be 9 there and 9 there and 9 there. So I'd have 27 in my group. That makes sense? If we do this one, the missing factor, help me write the problem. Missing factor.
12 divided by 8, and then
If I'm missing factor, I've got to change this from division to times, right? So what? 4 times what equals 12? The same answer goes in this blank as this, right? Over here, what is it? One third of what number gives me 9? If I were to take a third of what number would I get 9? So everybody, even with fractions, you can use these models. Okay? So I'm curious what some of you did for 7.3. What did you write for your what general procedure would make sense? And where did you get it from? The first one you did there was 7.3A1. Somebody give me the division problem. Which one is which? A1.
it's 1/2 divided by 1/6.
Is it 1/2 divided by 1/6, or is it 1/6 divided by 1/2? Is this right? Yeah. Because I have a remnant of this big. Each of the projects, what am I making here? Conference badges takes a 1/6. I want to know how many 1/6 there are in here, right? So how did you do this? Did you draw a picture? Cloth isn't in circles, but you can use circles, right? I've got a 1/2, and I want to know how many 1/6 are in there, right? Well, 1/6 would be this, and how many are in a 1/2? 3 is my answer, right? So what did I really do? I started with a half, which is 3/6, and I divided it by 1/6. And I asked how many 1/6 are there in 3/6? Right? And the answer is, there's 3. Which leads to this algorithm. If the denominators are the same, throw away the denominator and write the answer of the top divided by the top. 3 divided by 1 is 3. Throw away the denominator. Doesn't it? That's one algorithm that could come out of this. When you're saying, you don't need to get common denominators to divide. No. But when you do, doesn't it make sense that you just divide the top and throw away the bottom? Did anybody come up with that? So why is division of fractions taught the way it is now? And should we make changes in the way it's being made? I just want your thoughts. What do you think?
I think there needs to be changes. I didn't understand this in elementary school.
In elementary school? You couldn't keep change flip?
No, because it's not logical.
You could, but
It's not. I liked it.
It makes sense to me, I liked it.
what this here?
Keep change flip.
Oh, keep change flip.
Yeah.
That works for you.
I didn't have a problem with it.
Okay.
What I think it's great that we're changing to change it, but I think it's hard for the teachers because they grew up during the flip thing, and it's hard for us to change our minds. Like it's hard for me to wrap my head around this concept because I've been so trained to do the other thing. So I think it's gonna be hard for teachers to teach it efficiently to the students. If that makes sense.
Doing it the way we did it helps students to understand more about what division really means. You can do keep, change, flip, and you don't even have to know what division means, right? But to do it the way the students that use this curriculum do, they have to understand what division is. It means I'm going to do one of these models. I'm going to just repeatedly subtract this out, or I'm going to share it, or something where there's some meaning to it. And using diagrams and other things, you can successfully make sense of this in a way that if all we care about, I'll repeat this again, if all we care about in math are the answers, why even teach keep, change, flip? Just hand them a calculator that has fraction capabilities, show them where the divide button is, and go for it. But I think math is much, much more than that. It's about sense making and reasoning. And I don't know about you, but the first time I went through and did this exercise, it was like, that's making sense. Does that make? I hope you give your students that opportunity, because there's so much more to math than the algorithm of just crunching it. And with that introduction, we need to get going because we've got to cover a topic. I gave you not last night's homework, but the time before that's homework. I gave you a problem that said something like this. Okay. And the other one was? And I said, what do you think the answer is? So, what should we do here? This is clock arithmetic.
Okay, I don't
Casey?
know, but this is just a guess.
Okay.
So, would you start at 3 and then go like 3 numbers 6 times? Like,
What model is Casey using? Repeated addition. Did everybody hear what she was saying? So I get the clock. Clock 12. This is really a 0. And I'm going to go to 3. That's one group of 3. Then I'm going to go to 6. That's 2 groups. Then I'm going to go to 9. That's 3 groups of, okay. And how many groups of 3 do I need? 6. I'm not done then. There's 4 groups, 5 groups, 6 groups. The answer must be 6. Where did we start?
oh, we started at 0.
Started at 0, and then we did 6 threes.
Why would you start at 0 and not 3?
Why would you start at 3?
Because it says 3.
It says 3 times. Actually, 3 times 6 would mean we go to 6 and do it 3 times.
Oh, so we should start with
So start at 0 and go to 6. There's a 1 group of 6. 2 groups of 6. Then 3 groups of 6. Our answer is still 6.
The question, how do you know you start off with 0 this thing? Because normally when you're figuring out the time, you would start off whatever time you're at.
Don't do time. Don't do time. Do numbers. Do 3 plus 2. How do we do that? We start at 0 and we go 3. Then we go 2 more. But this is repeated addition. So we start at 0 and then we do however many groups of 3 or 6, depending on how you're thinking about it. Technically, this would be 3 times 6, not 6
So
times 3. But
they're not actually asking what time it is. They just want to know.
could be.
So you always start with 0.
Always start with 0 with this with repeated addition model. Yeah, we did with numbers. Why should we start anywhere else with? Okay. Does anybody have another way of doing it? That's great, Casey. To just add. Because that's what multiplication is, one of our models.
Another way is to do 3 times 6.
3 times 6, and we get what?
18.
Okay.
And then 18 divided by 12.
18 divided by 12. Why 12?
Because of the base.
Because that's the clock. And what do we get?
1 with the remainder. of
1.
6.
Remainder 6. And another way that we can call clock arithmetic is remainder arithmetic. And so we just write the remainder. That's another way to do clock multiplication. Multiply the two numbers in regular old 10. 3 times 6 is 18. Divide by the clock and write the remainder. Pretty easy. So we have 2 methods now. Repeated addition on a clock. Start Start at 0. Go around the clock as many times as this is, this far each time. Well, you can commute it and go either way. Okay? And the other way is to multiply the numbers, divide, write the remainder. Pretty easy. Okay. What about when it comes to division? What should we do here? Anybody have some ideas there?
Can you just, instead of adding, subtract?
One of our models for division is repeated subtraction. So, when we do repeated subtraction, where do we start subtracting from? Because it's really important where we start adding from on the multiplication model. You start at 0, right? Where do you start subtracting from when you do division? What did we do with regular numbers? If I do this with repeated subtraction, where do I start?
What's the number you started?
The
12.
dividend, right? Minus 4. Minus 4. Minus 4. And we stop when we get to 0, and then we what?
Just count how many.
Count how many times we did, right? So we stop when what?
Get to 0.
When we get to 0. Let's do it. Here we go. Where should I start?
11.
At the dividend, right? And we're going to go which way? Backwards. How big of jumps? 7. And when we get to 0, we'll stop. Ready? 1, 2, 3, 4, 5, 6, 7. Am I at 0? I'm going to just write this in here to keep track of how many times we've gone. 1, 2, 3, 4, 5, 6, 7. Am I at 0? Then 2 is not our answer. 1, 2, 3, 4, 5, 6, 7. Not at 0 yet. And I've gone 3 sevens. 1, 2, 3, 4, 5, 6, 7. That's 4 sevens, and I'm not at 0. 1, 2, 3, 4, 5, 6, 7. I went 5 sevens and I arrived at 0. My answer must be 5.
So your answer is 5 o'clock?
Yep. That's one way to do it, is repeated subtraction. On a clock. Starting at the dividend, going backwards in jumps of the divisor, and see how many of those jumps of that length it takes me to get to 0. That makes sense? It's just like numbers. Now, what else could we do? What other ways of thinking about subtraction do we have? Or excuse me, division. Missing factor. If this is the division problem, how could we write it as a multiplication of the same family that might make it easier to do? Help me. 7 times blank equals 11. This could be easier to do than a division problem because multiplication is easier than division. It's easier to wrap our head around it. How could we do this problem? Well, we could go back to what we were thinking of here. We could start at 0, right? And what?
Count forward in groups of 7.
Groups of 7, and see how many groups of 7 it takes us to get there, right? Well, 1, 2, 3, 4, I'm at 11. It took me 5, right? Now another way you could do it is you could just try this. You don't need a clock to do this. You could say 7 times 1 is 7. If I divide 7 by the clock 12, write the remainder, I get 7. Right? 7 times 2 is 14. If I divide by 12 and then write the remainder, it's 2. You with me? 7 times 3 is 21. Divide by 12. I get a remainder of 21 divided by 12. What's the remainder? 21 divided by 12. It goes in there. 12. 21 minus 12 is 9, isn't it? And we're looking for one with 11, so that's not it. 7 times 4 is 28. 28 divided by 12 goes in twice. 24, remainder of 4. I'm not at 11 yet. 7 times 5 is 35, divided by 12. Write the remainder. What do we get? 11. 5 must be the answer there. Okay? So, 2 methods. Repeated subtraction, starting at the dividend, jumping in groups of the divisor backwards until we get to 0, and the answer is how many jumps we made of that size. Or write it as a missing missing factor of the same family, and either use the clock or this to find your answer. And here's the third method. You guys have, some of you are still saying, I'm never going to do anything but keep, change, flip. So you'll take 2/3 divided by 4/7, and you'll rewrite that as 2/3 times
7/4.
the inverse of 4/7. What is the inverse of 4/7? Well, the inverse is the number that produces the identity. So I'm looking for the inverse for 4/7. So what would I times it by to get the identity? What is the identity? 1. What will I multiply by? 7/4. So I'm going to go up here and I'm going to replace the inverse of 4/7 with 7/4. And then I'm going to do the problem, and I'm going to get 7/6. So one way that we can do division is by multiplying by the multiplicative inverse. Same thing with clocks. We've done it 2 ways. What answer have we got both times? 5. Right? So 11 divided by 7 in clock 12 is the very same thing as 11 times, I better do it this way, times the inverse of 7 in clock 12. What is the inverse of 7? I don't know. So let's find out. The inverse will be the thing which when I multiply by it will give me the multiplicative identity. What's the multiplicative identity in clocks? What does nothing when I multiply? When I multiply by what, it does nothing in clocks. 1. It's the same as in regular numbers. Right?
What about the clock number? Wouldn't that also lead to the same?
If you multiply by that clock number, if I were doing it 0, I'm going to get 0.
No, I mean,
It
like,
didn't-
in
it
this
changed.
case, the clock number would be 12. So if you multiply it by 12, wouldn't it go around 12 times and create 7 with 0 remainder? Or is the answer 0?
There is no 12 in clock 12.
Ah, true. Never mind.
Okay? Everybody agree that multiplying by 1 in clocks doesn't change the number? Right?
Yeah.
It is the identity. So we're looking for, what would I multiply 12 by in clock? Let's see, did I erase? I did. We had 7 times 1 was 7. 7 times 2 was 2. 7 times 3 was 9. 7 times 4 was 4. And 7 times 5 was 11. But we haven't found one that is 1 yet. Let's keep going. 7 times 6 is 42. When I divide 42 by 12, I get a 6, don't I? Goes in 3 times, 36. 36 from 42 is 7 times 7 is equal to 49. Divided by 12, it goes in 4 times with remainder 1. That means that what? 7 is its very own inverse in clock 12. So, if 7 times 7 equals 1, then I can come up here where the inverse of 7 is, and I know what the inverse of 7 is. It's going to be 7. So that's the same as 11 times 7. Now, we can do that multiplication, any of the multiplication methods. We can do it on the clock, or the easiest way is what? Times them together. Get 77. Take 77 and divide by 12. 12 goes into 72 6 times with a remainder of 5. So I write the answer 5. And guess what? We got the very same answer we got through the other two methods. You ready to try another one? Okay. Here is 3 divided by 5 in clock 7. Any method you want. Okay. 3 divided by 5. If we use the clock, we start at the dividend, go backwards in jumps of 5 until we get to 0. 1, 2, let's see, yeah. 1, 2, 3, 4, 5. There's one jump of 5. 1, 2, 3, 4, 5. There's 2 jumps of 5, and guess what? I'm at 0. The answer must be 2. Based on the clock method, the repeated subtraction method on the clock. The other one is write a missing factor. Okay, here's our blank. And then see which problem fits. So 5 times 1 is 5. 5 times 2, that gives me 10 divided by 7 is a remainder of 3. That's the answer. So this must be 2. Because 5 times 2 is 10. When you divide it by 7, you get a remainder of 3. So 2 is my answer. So I agree. Now, dividing by 5 is the same as multiplying by the inverse of 5. But what is the inverse of 5? Well, I don't know, but 5 times that number will give me 1, right? So I came over here and I noticed I didn't have a 1 yet. So I just continued on. 5 times 3 and we hit the jackpot. 5 times 3 is 15. You divide 15 by 7, it goes in twice with a remainder of 1, which means that 3 has got to be the inverse of 5. Why? Because it yields the identity. That's why. Therefore, multiplying by the inverse, which we now know is 3, so I'm going to replace inverse of 5 with 3. I go 9 times 9 is 3. I go 3 times 3 is 9, and my brain's thinking. And divided by 7 goes in once with a remainder of 2. Notice this answer agrees with this answer, agrees with this answer on all 3 of them.
Now on the clock you started at 3.
Yep.
But over here you said you started at 0.
Nope. We started at 11.
Oh,
So
sorry.
we went back in jumps of 7. On multiplication, you start at 0 and you jump forward. Okay? What else? Let me give you one more here. Let's do... 1 divided by 3 and clock 5. You should be able to do it all 3 methods. 1 divided by 3 and clock 5. When someone gets it through any of the 3 methods, come on up. Okay, she went backwards on the clock, starting at 1, jumped back in groups of 3 until she arrived at 0 and got 2. Okay, Devin? Which method are you using? The missing factor? Okay. From the fact family? So where's your equation? Oh, from right? Okay. This one right here? Okay. Is that correct? Let's make sure we've got the right. If we want missing factor, you've got to use what operation, Devin? Now is she okay? Now she's all right. Okay, 3 times blank gives us 1. All right.
Still not right though, is
Well, you did 1, 2, let's see. You did 1, 2, 3 and got here. And then 1, 2, 3 and you got to 1. So 2 gets us to 1. Right? Somebody do the inverse method quickly? And have all 3? Did anybody do the inverse?
I tried, but I didn't get 2, so
Oh,
I got 3. I got 3.
Casey, come here.
So you do 1 divided by 5, 1.
5, 1,
Oh,
3
3 equals 1
Yeah, so 2 would be the
times
times 3 inverse 1.
the inverse of 3.
I can say that with 3 options 2. So, with your addition, which is like the...
Because 3 times 2 is 6, 6 minus 5 is 1.
Okay, so now keep going. Yeah,
So
I
the
have,
inverse,
that's my inverse is
the
2.
inverse is 2.
Yeah, so
Yeah.
keep going and then I don't.
So come up here, just rewrite this here. Put equals
Yeah, I was confused.
1
So you just...
1
Yeah,
times the inverse of 3 we found is
I added, never mind.
2.
It's like 3 times.
I put 1 times 2 is 3.
So 1 times 2 you get
Times 1 is 3.
2. You divide by 5, write the remainder.
So find the remainder
2.
to see what the same.
2 every time.
I did 1 times 2 equals 3. I don't
Ah.
know.
Yeah.
So I did the inverse part, right?
Okay, we'll give you a chance to practice. Two multiplication approaches and 3 different division approaches. Okay?